Hey guys, we'll get started in a minute or two once we have a few more people, okay?
Prachi, I just wanted to ask you, um, how different does like IB physics feel from like on-level physics that you took last year?
We definitely didn't learn all this like uncertainty stuff, so all of that is new to me. It's a little confusing actually. But I think once we get to kinematics, it'll be a lot more similar.
Yeah.
Because
Okay.
we started with, in regular physics, we started with vectors and then we did kinematics. And then we did dynamics and like so on. So the beginning is definitely different.
Okay. No, because the IB stuff is just the IB in general is a completely different mindset. You have to just approach it differently. So that's why I was curious, since I know like if you try and compare AP calculus with IB math, it's very different, like the course
Yeah.
structure.
I was talking to some of my friends who take AP physics, and they're not learning anything about like uncertainty and stuff like that. So they were like really confused when I was telling them and asking them questions about it.
The whole IB system was really confusing for me to figure out because I haven't like been exposed to it before. So okay, we'll just wait like another minute and then we'll get started. Okay, I think we can start now. I think more people will just like come and go as they want. So you guys have any questions?
I was hoping we could just um walk through like the graphing problems at the end of the problem set, like number 25 and onwards.
Okay, I didn't get a chance to try those because I had like meetings since
Sure,
school ended. But I can share my screen and we'll.
I think I get it. I just need some confirmation, just like just looking at other people do it and just making sure that I did it the same way. That's all.
You mean these, right?
Yeah.
Okay. Did anyone else do them? Because I know I haven't really looked at them yet.
I looked at them earlier, but I was really confused about all of this. So
okay. Yeah, this class was a little confusing. I know most of the stuff from the other two classes that we had, but this one was a little confusing for me too. I'm not really sure what it means by complete the process data table. I think it means to find the percentage uncertainties, because that's what it says here. If there's when she gave us this table and then later it had like percentage error. So I think it means to like process all of this and find the percentage error and write the distance with the uncertainties. So I guess our first step would be to average these. So you would average like this first, like, can you guys see my cursor or this like little hand thing?
We can see it.
Okay. So first you would like average these three values, right? And then you would do the plus or minus 0.3 seconds. Yes, yeah. So you would average these three because these are in seconds, and then you would do plus or minus 0.3 seconds.
Wouldn't the uncertainty then be the range over 2 though? So the uncertainty for once you average it and then you would have an uncertainty there, would that be 0.3 or would that be the 1.8 minus 1.5 divided by 2? Like that's when I get confused. Like when do you take the uncertainty of the measurement and when do you do the range, like the maximum minus minimum over 2?
I think you would add them because I know what she said before, like even if you have some uncertainty from a value, you might still have like human error. Like if you're pressing go on a stopwatch and then stopping it, you have that human error. So you would add that to the uncertainty of the stopwatch itself, right? So I think you would add them. I'm not sure, but that seems like the right thing to do here.
Like add the, so like I'm saying like for the uncertainty of the average. You know what I'm saying?
Yeah. The range,
Okay.
so 1.8 minus 1.6, it would be 0.2 divided by 2.
I think it would be 1.8 minus 1.5, right?
Yeah, right. Sorry.
Yeah, no, it's fine.
So it would be 0.45 seconds would be the uncertainty added together.
Wait, I didn't understand that. Wait, where'd you get the 0.45 from?
You would add so 1.8 minus 1.5 is 0.3, right?
Yeah.
Divided by 2, which is 0.15. And then if you add that to the uncertainty, it says up here, the 0.3, it would be 0.45.
So in the answer, it's in the solutions, it says that it's 0.2. That's why I got a little confused because it's just like when you have multiple trials, do you take the average and then that's it? Or do you take the range over 2 and then add it back to like you were saying? Because there's just so many, like, I'm not sure when to do what. I think that's.
I don't know. I mean, it seems from what you said before, it seems to me like we should add them, but then that doesn't match the answer key. So yeah, I don't know.
Same with the other ones. Like if you do the other ones, it's just, yeah, like right there, it's just 1.6 plus minus 0.2, right? That's why I got a little confused. Maybe if we test it out with the other ones, that might help. So like if we did what? Like the next one would be what? 2.3 minus 1.9?
Yeah, so 0.4. So
over
0.2. So then it would be 0.5, but I don't think that's what that. Yeah, it only says 0. It's
just 0.2. So maybe it's just you take the range over 2 if it's multiple then. So when would you add it? So I'm guessing you would add it only if you're like adding different values, right? Like not taking the average then.
Yeah, I mean you do add them if you add different values, but then where is this uncertainty from? Is this not from human error or?
That's from human error, I think. But see that's why I asked in class about that today, and I didn't really fully understand it. But I think what she was saying was ultimately that uncertainty, like, I guess that uncertainty wouldn't matter ultimately because you're taking the range over 2 or something. Like that's what she said. Like she was talking about the range over 2, but then I got confused because what does the original uncertainty mean then? You know?
Yeah.
Does anyone else remember about what she said about this? About like the range over 2? Okay.
I thought maybe it would like still say it on the finish table if it still said it here like plus or minus 3. Plus or minus 0.3, then I thought we might not have to take it into account, but it doesn't say it here either.
Okay.
So, yeah, I guess we don't know.
So then percentage error is just, go ahead.
Go ahead.
No, I was just saying percentage error would then just be the uncertainty over the average, right?
Yeah, I think we would use the uncertainty that we got from the range over 2, because that's what's used in this table.
In that table.
So for now, I guess we can just go with the range over 2 for these tables. I'll probably like go to her office hours tomorrow and ask about this.
Okay, sounds good. Cool.
Okay, should we just go through the rest of these? Does anyone need to review like from the topics that we did before, like maybe like adding and subtracting and like how uncertainty works for those and multiplication and division?
I have a question. So I know that she said that you want to round to one sig fig whenever you're doing uncertainty, but on the answer key, there were a lot of times where there were like more than sig.
Yeah, that confused me too. I wasn't really sure. I know at one point it says in the PowerPoint, it says that normally there's one sig fig, but then it said like this year you're allowed to use two. So I think it's okay if you have two. It just
For the
it
test, should we put
several times.
so for the test, should we put one or two?
I would put one just to be safe. I was
Yeah.
gonna put one just because
That's what
that's what's generally accepted, I think, from IB. So
Okay.
And then the other thing I noticed was like it can't be like, so if your increments, like if your precision is 0.1 and you have 0.15 in your uncertainty, that can't work because like the precision of the uncertainty can't be like greater than the precision of the original instrument.
yeah.
She was also mentioning that. So then you would have to round that to, I guess, 0.2. So I get confused when you round to one sig fig, but it's still, the precision doesn't match like, there was a problem, I think. I can't remember.
Are you talking about like the precision of the instrument versus the precision of the measurement?
Yeah, so like how do you round, like the rounding is where I get confused a lot.
I mean, I guess it's always hard to like round up, right? You would just round up to however many sig figs you need, and then you would add it.
So you round to one sig fig, but then there's like caveats where if the precision of the instrument is less, then you round to that precision instead of the sig figs. So it's still one sig fig, but you have to decrease the precision, and that's when I get confused. So like, with like when they were measuring the resistance, if you have 609 ohms, 666 ohms, whatever, and we round to one sig fig, it's 30 ohms, right? But say for example, this wouldn't be possible, but say for example the precision of the measurement was 100 ohms. It wouldn't even be possible, right? But say it was 100 ohms, then what would the answer be for that one?
It doesn't 100 be one sig fig, so wouldn't it just be 100?
So that would be the precision, but then our uncertainty right now is 30 ohms, right? So would you round that to 0 ohms then? Like those are the scenarios where I get confused.
No, I think because it's precision, it's better to have too much of a range on either side than have too little. Because if you say 0, then you're saying that my answer is perfect, which it's not. So it's better to have 100 ohms of uncertainty than have 0. Because 0 is not
okay. Got it. That clears it up.
Although that would be a very strange measurement.
Yeah, I mean it's a hypothetical situation. I mean, obviously we can see the precision is 1 ohm here, right? So that's our problem.
It confused me too, where I was confused about like which decimal place to round to.
Yeah.
And for those, I guess I just kind of I just went through all the questions, and I was like looking back over and just like finding like patterns, I guess, of like how she rounded like for the answer key, because it's not always like the exact same. So I think you just have to like once you do all of them, just like go back and look at them, just try to find some patterns of like how she did that.
And then can we try number 35 together, because I got the answer one way, but it's like really confusing for me. Number 35, like it has to do with linearization.
It can be shown that the graph of V equals RE over R plus R, where E and R are constants. In order to obtain a straight line graph, one would plot a graph of. Right, these were confusing for me in class too, because I was, the one problem where she says that you would graph something against 1 over t squared. I was like, how would you get a straight line from that? Because it doesn't seem like it would produce a straight line.
Well, I got number 36. Number 36 was fine, because if we have t equals 2 pi root m over k, right? Our goal is to get it in the form y equals mx, right? And x can be L squared, it can be root L, whatever, but it just needs to be in the form y equals mx plus b. So that means we need to find a way to separate a constant and then separate the variables. So if we do that, we can think of, like I think we actually did this one in class, right?
Yeah, we did.
Where it was,
Find it.
I think the answer choices were a little bit different.
It's right here.
Yeah.
Too much.
T equal, yeah. So what we said was you would square, you would write, your constant would be 2 pi over root k, and then essentially that's t equals some constant times root m, right?
Yeah.
So then that's why the answer there.
You have to get m like on its own. Like there needs to be a constant in front of it.
So similarly, if we try the same approach in the other one, that was confusing, like the RE over R plus R.
Yeah. I think,
The E you could take out, right? Because it's a constant.
Yeah, I guess you could multiply, but then the only problem is then you have R on both sides.
It's that R in the denominator plus the little r that's messing this whole thing up, right?
I know.
You know, maybe, since it's in the denominator, we're having trouble with it because it's in the denominator. But what if we flip the fraction? So we take the reciprocal, yeah, we take the reciprocal of both sides. Then it'll be 1 over v equals 1 over e times big R plus small r over big R.
Wait, what did you say about 1 over e? Wouldn't R and E both just go to the bottom? Okay, you could separate it. Yeah, I see what you're saying.
Yeah, so I was trying to separate it out.
Yeah.
So
you still have that little R.
No, but the benefit of this is here. Can I annotate on your screen?
Yeah.
So here's what I was thinking, and I'm not sure if this works, but you start with v equals e times r over big R plus r, and then if we take the reciprocal of both sides, we get 1 over v equals 1 over e times big R plus little r over big R. And now we can separate this out, right? So now we can say 1 over v equals 1 over e times 1 plus r over r, right? Now here's the tricky part.
Honestly, could you divide the whole thing by r, by a little r? Just so you would have 1 over r.
Yeah, that would like from this step or this step?
From the last step that you did. Because basically we're just trying to get r on its own. Like it's okay if it's in the denominator, it just needs to be on its own with no other variables.
I see. Okay, yeah. So if we divide everything by r, then
would that divide the 1 by r to like just the one that's inside the parentheses? Would that be 1 over little r, and then 1 over e times little r?
So you're saying do an r here and then put an r here, and then that gets rid of that r, is what you're saying? Wait, no, that doesn't make. Wait, I don't think I did that right.
No, I was saying if you divide by the r that's inside the parentheses, would it also divide this 1 by r?
Yeah, you would have to, I guess, because you would have to divide this whole thing by r.
But then it would also be in the v. Doesn't the v also have to be on its own?
So yeah, so instead what we can do is if we divide this whole thing by r, we can just put the r in the numerator here. Essentially what we're doing is we're multiplying by 1, right? Because that r and that r will cancel. So instead of multiplying or dividing both sides by r, approach it as multiplying by r over r. That's why I put the r here, and then I divided by r.
So then where is our big R still there, or is it?
So then what would happen is this, we can view this as 1 over v equals r over e times 1 over r plus 1 over big R, right? And what this allows us to do is now we can say 1 over v equals, so this r, so now we can distribute this, and this will be 1 over e, right? Because this r and this r will cancel.
When you multiply by r over little r, wouldn't they become r squared over big R? Or no, actually they would cancel, never mind.
Yeah, so I'm saying, yeah, I'm saying like,
okay, I see it, yeah.
So now the thing is, we have this times this plus R over E times 1 over R. Okay, I think we're in the format
that's
that we
mx
need,
plus
right?
b.
Yeah, that's mx plus b. Yes, sorry. There we are. Sometimes you don't even realize when the answer is there. So that's y equals this R over E is a constant. That's our m. 1 over R, big R is our variable, right? So that's x. And then the 1 over E is our b. And that's why I guess it would be 1 over v and 1 against 1 over R.
And
I hope we don't get a problem like this.
Right?
That's really, yeah, that would be C.
That was a really hard problem though. I hope we don't have that on the test.
It's like that's very math heavy. Like
okay, so we got it right.
Okay.
Okay. Wow, that was confusing.
So I guess the way to approach these, I'm thinking, is just the ultimate way to do it is just find it, like try and separate out the constants from the variable.
You just have to like play with the equation until it turns out correctly.
Okay.
But how much time do we have to do this test? Do we know? Like, is it timed, or do we get the whole time to work on it? Because
probably the whole
is a
class.
very time-consuming problem.
And I mean, usually if it's like, if the majority of the class isn't finished, I mean,
yeah.
Like if she says that, like, I know we had a quiz, and if it was like 20 set for originally 10 minutes, I know most of us weren't done after 15, so she gave us a few more minutes. So she's lenient with that. So I think she'll give us the whole class probably.
Okay.
I have a question about linearization. So like, why do we do the linearization? Like, I don't understand.
I think it just makes the data easier to see, and it's easier to like find the slope. So it's easier to find relationships and like see the relationships between the variables. Because if you have a graph that has like not I don't want to say even slope, but like an easy to see like slope, then it's harder to say like, oh, this variable relates to, like, the x relates to y in this way or this way. So I think the linearization, because we're so, like, linear equations are the easiest ones to see, right? So I feel like it just simplifies it. It's an easier way to present the data.
So is it just the line of best fit for a not linear equation? Is that what you do to like find, like, do the linearization?
For the linearization, you have to like get the variables on their own, like we just did with number 35, right? And then once you have them that way, then you can do the thing she was saying about the greater gradient or the lower gradient. I forgot what the exact words were, but the gradient lines. So once you do the linearization, like the problem that we just did, after that you can plot the points, and then you can find those other lines that she was talking about.
Oh, okay. Thank you.
Can I share my screen? There's something I remembered from AP Chemistry that I learned last year.
Yeah.
Can you enable screen sharing?
Yeah.
So what I remember is there's like different orders of reactions. There's like first order, second order, and third order reactions. So like if your rate equals some constant versus rate equals some constant times the concentration versus rate equals some constant times the concentration to the second power. Do you see how those are different? Then I didn't realize we were actually linearizing it, but we used to plot it differently. So like we used to plot we used to plot the concentration against T. Then for first order reactions, we used to plot the natural log of A against T. And then for third order, we used to plot 1 over the concentration against T. And that produces straight lines. And that allows us to calculate the constant K because it's a straight line now. Versus if we had directly plotted the natural log, it's not a straight line. So I guess what this allows you to do is kind of just see the rate of change more easily, I guess. Because I know in AP Chem, the focus was really on graphing and finding, plotting it properly. Oh God, it's raining really bad.
Yeah, it's raining here. That's almost exactly the same thing that we're learning here, right?
Yeah.
Okay,
I think we have about 5 minutes left. So if you guys
I'm still a little confused on like instrument uncertainty versus like absolute uncertainty. So like, what's the difference between those?
Let me check the PowerPoint. I don't want to say something wrong. I think instrument uncertainty is like however much the instrument measures, you divide that by half, because that's how much you can like see from that instrument. For analog instrument, like for a ruler, you would do like the smallest, like if the ruler measures by centimeters, you would do 0.5 centimeters as the absolute uncertainty. No, the instrument uncertainty, I think.
Oh, okay. So if it gives you the equation and if it does, so if like the uncertainty, the absolute uncertainty is like 0.1, then the instrument uncertainty would be 0.05.
I don't think you can't find the instrument uncertainty from the absolute uncertainty. You have to like look at the instrument. Like if you look at this like ruler that's here, it measures to what, like 1 millimeter, I think. Right, and so you would do 0.5 millimeters, I think, for this. That would be the instrument uncertainty. And then if you go, I know there was a picture of another instrument. It was a digital instrument, this one. So for this, the instrument uncertainty would be 0.001, because that's how far it can measure. So for analog instruments like a ruler, or like maybe like a protractor, something that you use to measure degrees, for that it would be half of whichever like degree it can measure to. And often for a ruler, and maybe also for a protractor, you double it because it's uncertain on both sides. Because wherever you start measuring on the ruler, that side is uncertain, and then wherever you stop measuring, that's also uncertain. So technically you have to half it, and then you have to double it again because it's uncertain on both sides. Does that make sense?
This would only be for like single measurements, right?
Yeah, this is only for single measurements. For averaging, it's different.
So, okay, so as soon as you take more than one trial, then you have to revert to the averaging and then the range over 2 method, right?
Yeah.
Okay.
So then that kind of like, so the absolute uncertainty would be the one for the instrument, I think, and then for single measurements. So then once you start adding and subtracting and like averaging and stuff, for averages you do the range of the values over 2. That's your uncertainty, because that's like that shows the complete range of values that you had before you took the average. Does that make sense? I feel like I didn't explain that very well.
That makes sense, yeah.
Yeah, it makes sense.
I know we only have like 2 minutes, but can we do one of the multiplication problems for the uncertainty?
I think it's okay if we run a little bit over, because the meeting is for 40 minutes. So which one do you want to do?
I'm fine with either. I mean, any of them. I'm just a little confused with like how you have to multiply the uncertainties you get by the actual value you get after. I don't know. I'm just a little confused.
Because I think you're talking about percentage uncertainty, right? It's because it says like if you have the percentage uncertainty of one value and then you have the percentage uncertainty of another value, when you add those uncertainties together, you get another percentage. So then you have to actually apply the percentage to the value you get to get the real uncertainty.
Oh, I didn't even realize we were getting percentage uncertainty.
Yeah.
Because they're fractions. Oh, okay. That makes so much more. That just makes so much more intuitive sense when you think about it as like percentages rather than, because I mean,
I was confused about a lot of these, and then I realized I was like, why are we applying this? And I was like, it's because it's a percentage, so you actually have to apply it back to get the actual value. That's why you multiply it
back to that final result to get the. Okay, can we try number 8? It has to do with speed. We're given distance and time.
Yeah, I actually did this one. Okay. Yeah, I actually got this one wrong at first because I forgot to do the multiplying that we were just talking about. So I had to go back and do that. So first you would just divide the regular values. So you would do 64.7 over 8.65. And I think that gives you 7.48. Because when you multiply or divide, you go with the smallest number of sig figs, right? So you would stay with 3 sig figs. So you would get 7.48 for just the value. And then you divide 0.5 this uncertainty. You you divide this uncertainty by the value, right? And you would get about 0.0077. And I didn't really round like while I was doing that. I kept the values as long as I could without making it too complicated. So for this one, for the percentage uncertainty, I got fractional uncertainty, I got 0.007. And for this one, I divided 0.05 by 8.65, and I got 0.0058. So those two are the fractional uncertainties, because when you're multiplying and dividing, you can use either of them, fractional and percentage. They're both similar. So, and then if you add them together, you get, what do I get? I forgot.
Yeah, I just put them all into the calculator at once. Like, I'll just put in like that whole thing, parentheses, 0.5 over 64.7 plus 0.05 over 8.65. Do you think we need to actually write out the step-by-step?
I don't know. I like writing out the step-by-step just because it helps like me keep track of the values, and it's just easier for me to see it. But I don't think you have to. I don't think she's gonna make you do it because you're putting in the calculator anyway. So
what if she gives you partial credit? What if just take the partial credit for?
Yeah, you might as well write it down. I mean, if you can.
Oh, okay, yeah.
Whenever I put the long equations into the calculator, I know I mess up on those a lot. Like I'll forget to put a parenthesis somewhere, so I try to avoid those if I can.
I see. Okay.
So if you would add the fractional uncertainties for these two, I got 0.135. So that's like the fraction of uncertainty of the final value. So then you multiply 0.0135 by 7.48, which is what we got when we divided the actual values, and you get 0.1 for the uncertainty. So the final answer would be 7.48 plus or minus 0.1 meters per second.
Wait, so I got 7.5. So I would round. Wouldn't you round the first one the same precision as your uncertainty, or can you leave it at 7.48?
They did.
That's another area where I get confused.
Yeah, I was confused about that too, because on the answer key it does say 7.48 plus or minus 0.1, and it's because it's not the same sig figs and it's not the same precision either. And I was confused as to where she got that from, but I haven't asked her about it yet, but I probably will ask her about it because it seems inconsistent, and I'm confused why that is.
Yeah, it's just like there's little inconsistencies here and there, and that's just in my understanding. I think it's just somewhere I'm not making a connection where I need to be.
I'm just afraid I'm gonna put like the wrong amount of sig figs on the test, and then she's gonna take off points. Okay. And I really don't want that to happen. So.
But I feel like if that's a final step in the process, it won't be that like it'll just be part of it. So, but yeah, it's better to have everything cleared up than to.
Yeah. So I'll probably go to her office hours tomorrow with all these questions, and then I'll say in the channel I'll put a list there of what she said.
So do you guys remember like exactly when to like round to 1 sig fig, or like what we need to round to 1 sig fig for every time?
Generally, she said for the uncertainties, she said that IB says that you should round to 1 sig fig, but then it also has like twice there's like a little note to the side where it says this year rounding to 2 sig figs is okay. So like we're not really sure about when to round to what number of sig figs. So I'm gonna go ask her, and I'll definitely put the answer into the physics channel. But right now, I guess we don't really know.
Thank you.
Yeah. Okay. Are we done? Does anyone else have any more questions? We have about 5 minutes left in the meeting.
Well, if no one else has questions, I just want to remind everyone you could subscribe to the YouTube channel for Revise Now. That would be good. Just so we can, if you can sign up that way, we can extend our reach a little bit more. And then feel free to claim CAS hours for this, because this can definitely count towards creativity if you need that. And the forums are on the Revise Now chapter website that Prachi posted in the physics channel.
I have a little bit of like an unrelated question about CAS hours.
Okay.
So like,
Prachi, can you end the recording? That way we don't prolong the recording.